So I have some good questions during the break. I'll address some of them later. So where are we now? So Bill is trying to design this convincing device, that's a device that will convince me to trust him. So where we are is that I know at least when not to trust him. And so that we specify that if we run the Bell test and we estimate this value S, and if it is somewhere between 2 and -2, that means do not trust Bill. Give him devices back and, ask for your money back. However, that's Bill, of course, knows this. And so he would never design devices to disappoint you, in this way at least. So therefore, we are now, so let's look what's going to happen. First of all, maybe because some of you ask, what is actually the meaning of this? Can we just put a little bit more of intuition to S? It just popped up like this. Yes, we can. So a good way to think about it, in fact, the test I'm going to run eventually is not going to be really like estimating S, but I'm going to do something else. And so the test, CHS test that we like these days goes roughly like this. So you have those two devices, you input X, you input Y here, and you get A and you get B from this device. And of course, so you have different values of A and different values of B. And what we are looking at something that is call it CHSH condition. Namely, we are looking for cases or instances where A and B and X and Y satisfy the following condition. A plus B in binary is equal X times Y. So what does it mean? It means that we want A and B to be identical in all cases for all inputs except when you input 1 and 1. When X is equal to 1 and Y is equal to 1, this product is equal to 1, and therefore you want A and B to be different. Now let's look at this condition in more detail. So by the way, thank you for bringing this up. So this is, if there's a Boolean function, if Bill has instruction, can he satisfy this particular condition with a set of instructions in the box? So if I have a specific value A0, I want this to be equal to B0. And if I have, sorry, let me just write also A1 here and B1 here. And I want B0 to be equal to A1. And I want A0 to be equal to B1. But I definitely, when I have two inputs which are 1, I want them to be different. So as you can see that this condition is impossible to satisfy if I have a specific value assignment, if there is a prescribed set of instructions in the box. At best you can satisfy this condition with probability 3/4, right? So it's clearly that 3 of those sort of conditions can be satisfied, but not 4 of them. So you cannot just have an input, a predefined input, prescribed input in the box that does the job. So your probability, so essentially the Bell test, the CHS test, is carry on generating numbers, outputs A and B, and look at them and count the number of them that this condition is satisfied, okay? If there is a predefined set of instructions, this number will not be more than 75%. So below 75%, Bill may know what's going on. Above 75%, and that's where things become interesting, things can happen, and we'll talk about this. So the two, this rate, omega, is related to this S. It's, so omega is 1/2 plus 1/8, this average S. So S kind of, so physicists prefer to evaluate this value S for historical reason, but you can then translate in terms of those things like, let's translate this condition that we have, this one here, in terms of variables of the plus and minus one type. What this condition says essentially is that you want AX and BY to be equal to 1 for X and Y. Well, yeah, they have to be identical when the product is equal to 0, and then they have to be equal to -1 in this case where X is equal to 1 and Y is equal to 1. So therefore, in terms of the CHSH inequalities, this condition sort of goes to, so this estimated value of S, which was A0, B0 plus A0, B1 plus A1, B0. And I had this minus sign, and people were sort of like asking, why do we have minus here? And this minus is explicitly related to the fact it's taking this condition and mapping this to S. And that's why where things are supposed to be different, the minus sign appear. And so you have A1, B1. I'm probably not doing the best job explaining this, but see what happens if this condition is satisfied. So if this condition is satisfied, omega, the probability that you get it right in every single round is going to be equal to 1. So this expression is going to be equal to 1. So S is equal to 4, you're 4, right? So that is hypothetical scenario. If you could build boxes of this type where omega is equal to 1, so every single time you satisfy this condition, which is obviously weird, right? Because we can see that this cannot be satisfied by a value assignment. If you pre-program, you'll never satisfy it. So anything more than 75%, you're already puzzled. And getting to 1 is amazing, right? So that you can do it. And translating this into this S, you can see that for input 0 and 0, this should be equal to 1. This should be equal to 1. This should be equal to 1. However, for input 1, 1, we have the product AX BY minus 1. So therefore, we have plus 1 essentially here. So here 1 plus 1 plus 1 plus 1 equal to 4, consistent with that. So this is just to say that this kind of a box of that kind can actually never be built, or at least to the best of our knowledge. Even Bill cannot do it. So what Bill can do is to go with this probability up to roughly, so well, we'll come to this, but just to give you a spoiler, so omega, where shall I write it? So here, omega can be smaller than 0.75. So that corresponds to average S less than 2. And that's okay. So that's a classical scenario. Bill can know everything. But the next thing is Bill can actually push omega a little bit further to 0.85, I think. So that corresponds to S to square root of 2. And then going to omega equal 1 is a heroic effort, not possible yet by any known technology. That would give you S equal to 4. Okay, but let's this will be also more clarified soon. So we are at. Are there any questions about this, by the way, so far? So what I'm saying is that the best way to run the CHSH test is in fact not to evaluate S, but to evaluate omega. And then you can get, if you're really after, everything can be translated, expressed in terms of omega, but there's a whole body of knowledge by, generation of physicists before you and before me worked hard on this, and they usually work with this figure of merit S. So that's why it's much easier to actually calculate omega if you want, but express it, then look at S, because there are many results which refer directly to S. Not a big deal, because, that's a very simple formula to go from one to the other. But conceptually, it's much nicer to think in terms of omega in this experiment. You simply just generate those pairs, and you look how many times this condition is satisfied. What is the success rate in this called CHSH game? If it is above 75%, Bill might be doing something right, and I may be buying this device. If it is below 75%, no way. Okay? Okay, so now let's say over 75. You look at the case below 75%, over 75%. What's going to happen here? So let me just then go back to this probability distribution P that I wrote as a matrix. So by the way, there was a person called Cyrelson who looked at it from the mathematical point of view. This name, at least I know how to pronounce. He was a Russian, Jewish, Russian Israeli. His name is Cyril. And you don't write it this way?
I don't know. I mean, I know the Russian spelling.
Yeah, well, Cyril, maybe that's just a different transliteration. You say, how do you pronounce?
Cyril.
I think, say again. Cyril. So this is like. Okay. Anyway, so if you look at Cyrelson, if you look at, look him up. I think, but by the way, I understand that if you use Cyrillic, it's probably written differently. But I think in the literature that his name was transliterated this way.
Yeah.
Okay.
Some letters that don't exist in the
right. Okay. So Cyrelson, and why did I mention that? Oh yeah, he worked on this stuff a lot, and there are lots of interesting bounds. So look him up, by the way. So if I have this matrix P that sort of describes behavior, so I wanted to say that Cyrelson used the term behavior for this kind of a matrix which kind of contains 4 different probability distributions. So because it describes the behavior of the boxes completely. And can we extract this figure of merit S or omega from this? Of course we can, right? Because all the information about the behavior of those boxes is in this probability distribution. You have like 16 different numbers here, not all independent. 8 of them are really independent, but this is a lot, and we don't need that much. We only need one number, either omega or S, to make statements about Bill. So Bill is not as complicated as 8-dimensional real Hilbert space, right? Well, sorry, Bill, I know that. No, it's okay, Bill. So just one number will tell us something about his intentions. And so we can, of course, extract it from here. So how do we get S, or how do we get omega from this matrix? So if someone shows you this matrix, or you estimate, even though you don't have to, because you'll be doing too much work, omega is just simply a probability of satisfying this condition. And you can check that you simply have to add those terms here, those two terms on diagonal, those two terms on diagonal. And because of this flip in x equal, so for x equal 1 and y equal 1, we have to satisfy, they have to be different. So that's why you have to be adding off diagonal elements here. So this is how you get omega. So in other words, and how do you get S? Well, you get S by having omega with having plus here and adding those terms as well, but with a minus sign. So in other words, I can, let me just write this way. If I have a matrix which is of this type, plus, plus, minus, minus, plus, 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 minus, 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 plus, plus, minus, minus. So it's plus 1 minus 1 matrix. So S can be written, the value, sort of like the mean value, expected value of S is written as, for a given probability distribution describing the boxes, can be simply written as, let me just write the expression first, and then how shall I call this matrix? Call it V. Trace V dagger P. Let me just explain what it means. So this you may know as a sort of like a inner product. It has a fancy name, but it's actually a very simple thing. It's called Hilbert-Schmidt product. Inner product or scalar product. So what it does essentially, so if you have a matrix P, it just, you go element by element, and you have a linear combination of this element with plus sign, this element with minus sign, this element with minus, this element with plus, and so on. So let me maybe just explain. Maybe it's just worth knowing this stuff because they always look complicated, but they are not. Especially they look very fancy when you just put names to them. They always have fancy names like Hilbert-Schmidt product, you know, just you want to impress someone. But it's actually as simple as a real product. So for example, you take a scalar product, you have two vectors, okay? A and B. Sometimes you may want to write a scalar product this way, or you may want to write it this way. But in terms of components, you write it as sum over K, AK, BK, right? But now suppose you have, your K is composed of two indices. So it's going to be, it's still the same thing. So you say, okay, if K is a pair Ij, so it's going to be a sum over Ij, A, Ij, B, Ij. Still the same thing, right? It's just, instead of K, I just have a pair of numbers Ij, and I just sum over everything. So that's the scalar product. But then you say, okay, that looks like a matrix to me. Of course, I can take any numbers and tabulate them into a matrix. And I can write the whole thing here as sum over J. Think about it as a matrix AT, JI. So I take transpose, I flip the indices, and I have B, Ij. So then sum over I here. So what do I have here? I have a product of the two matrices. And so that's a product of A transpose with B. And this thing means I have to take the trace of the whole thing, right? I sum over J. So it becomes trace without going into indices, is just a trace of A transpose multiplied by B. So this is quite often we write it this way. It's just a scalar product of two matrices, but it is a scalar product. It's just there's nothing fancy about it. Of course, you know, once you want to get a certain mathematical sophistication, you can think about the operators, define it in a proper way, yada, 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 and there's a whole body of knowledge about this. But to us, in finite dimensional Hilbert spaces, actually we're talking about the finite dimensional real spaces here, it's just a scalar product called Hilbert-Schmidt product, and fine. And so I'll be using, so if I, and what it really means that if I have two matrices, so you see, look at this. What it really means that if I have two matrices, I just multiply this term with this term. So it's going to be a multiplication term by term, entry by entry. So this with this, and so on. And then just add them together. So in this case, you can see that it was maybe a long explanation, too long, but all I wanted to do is that if I define this matrix V with plus and minuses, so that I can express the mean value of S simply as V acting on, and this is the matrix describing the behavior. So this is this four-dimensional matrix which tells me which entry to pick up from the probability matrix and how to add them up together, some of them with plus sign, some of them with minus sign. And as any inner product, this also defines kind of what is called a functional. It can take any P, any probability distribution, and give you a number, right? So it's like inner product defines functional, so like a linear form. You just take a vector, and then the inner product will, with another fixed vector, will give you a number. So that's the reason I'm telling you this story, because I'm going to now for a graphical description of the whole thing. So if I have if I have those probability distributions, I can think about it as a point in Euclidean space, which has dimension R16. There are 16 numbers, so it's kind of a space, and this is the probability point, and all behaviors form a convex set, right? And you saw this diagram before. Where so think about this as a space of all possible probability distribution of this type. Some of them are here, some of them are here, and so on and so forth. So what the Bell inequality tells you, so the Bell inequality says that this thing here means that if I take the functional, so this functional here defines the hyperplane in this space, right? So imagine that if you take Vp equal to +2 or -2, so that will select all vectors, all probability points, such that the value of this function is fixed. So this is exactly the geometrically speaking. So this Bell functional tells us that the Bell statement tells us that in this probability space, we have two supporting hyperplanes, and all classical, all devices that are dubious, that you shouldn't be buying, are sandwiched in between those two hyperplanes. So the inequality means that that all those points are somewhere here. Now, what's going to happen if, and by the way, a linear functional, as long as I can represent the probability distribution as a point, how do I represent the linear functional? Like by linear functional meaning this thing, waiting for vector P or probability point to come and to become sort of V acts on P and becomes a number. So of course, you know, the functional is defined as a set of a parallel hyperplanes with, so this could be S equals 0. And so we have a hyperplanes that define a linear functional this way. So those are called Bell functionals. People who study those things can study all kind of different Bell functionals. They don't have to be of this type, and also had discussion over the break. But this is the most common functional. This figure of merit S corresponds into this particular functional. So the geometric picture is that you have a convex set somewhere there, and then you can, between this sort of a Bell functional defines you the range of points in the set where things are classical. Now, if you go over the set of, so if you go above, you can still continue, and we know that at some point you reach the maximum value of this functional on the set of quantum behaviors, and at this point you get 2 square root of 2. And you know, I can describe you probably know how to generate 2 square root of 2. You have maximally entangled qubits and you perform simple measurements on them. So there is a simple procedure that allows you to go with S equal to 2 square root of 2, and that corresponds to omega, as we are talking, which is roughly, I think is equal cos squared pi over 8 at this point, which is roughly 0.85 something. So the interesting thing, the reason I'm telling you about those linear functionals is that so if you have a convex set of any type, see, I assume you know what is a convex set, right? Something that is, so this is convex and this is not convex because I can have 2 points that somehow, if I connect them, there is a point somewhere on this line that is outside the set. But in this set, it's a convex set because for any 2 points that I pick up, and if I connect those points, the whole segment lies in the set. So, of course, you know, those points in our case represent behaviors of the boxes. And if I have 2 points and the line in between, I can have a convex combination of behavior of the boxes. That means, for example, with certain probability, Bill is generating boxes that behave in this way, and with some other probability, the boxes that behave in a different way. That is also a valid behavior. So the convex combination of behavior is also a valid behavior. That's why the behaviors form the convex set. Now, the interesting thing about the functionals on the convex set, so if I have a set of parallel lines, so if I pick up the functional, so those are, you know, inside the set, there are vectors, there are points, behaviors, P. Now, functionals are defined by set of parallel hyperplanes. So I can have parallel, you know, the set of planes going this way. And there is a theorem, but it's so intuitive that you don't even have to prove it, which says that if you have a functional the maximum value and the minimum value of a function over a convex set is always achieved on the edges at the external points. So in this case, you can see that if, for example, the values of the function go this way, so you may have 0, 1, whatever, 5, 42, right? So if they just increase in this way, so then the minimum will be somewhere here. You'll have a supporting hyperplane touching it here. And the maximum value will be also on the edge. You will never get any maximum or minimum or inside the convex set. And what is interesting is, except those cases where we have hyperplanes that sort of form a polytope, if the set is not a polytope, this point is unique, right? So you go in this way, and there's this one point at which, you know, for this particular value that defines the behavior. So why is it important? Now look at this functional S. It goes this way, so it goes from 0, the messy system, the boxes generate numbers at random. And then we are still in the build domain. Build domain goes to S equal 1. But then, the function increase in this direction. So we start with S, and we go here, 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 here. At this point, we have S equal 1, you know, on the border. And then we start going into the quantum domain. And at some point, the function goes to the maximum value. Now, of course, I have to prove that this is the maximal value, but it's called Zirelson bound, right? Zirelson bound. So this thing is Zirelson bound. And it is 2 square root of 2 in terms of S, and it is equal to cos squared pi over 8 in terms of omega. But we are now talking about the functional S. So this function gets the maximum value at this point. And why is it important? Because when it gets the maximum value, then there is just one behavior there. There are not many, but there's just one. So if I get devices from Bill and I run the CHSH test and modulo noises and, you know, everything, I get S equal to 2 square root of 2. That gives me hell a lot of information. That gives me information. Bill was absolutely honest with me. He provided the best device he could. And in fact, I can even infer from this fact, because this is a unique point, up to some local unitaries or local isometries that do not matter, how those boxes work. I know, and you know, there's a little bit more to show this, but to cut a long story short, at this point defines behavior pretty well up to some local isometries. And in this case, I know how the boxes work. I don't have to look inside. I simply know what is inside, because there's no other way to reach that point but to violate the Bell inequality using maximally entangled states with a given choices of variables. So in other words, I know at this point that the boxes contain entangled qubits in, say, state 1 over square root of 2, 0, 0 plus 1, 1. And in terms of the, if I were to draw Pauli vectors describing the variables, they would look like this. So that would be the measurement Z corresponds to 1, the measurement X, and this would be Z minus X and Z plus X 1 over square root of 2. So I know, at this point, I know exactly what, if I press X, if I choose X equals 0, this box is measuring Z, if I put x equal 1, this box is measuring x. Here, depending whether y is equal 0 or 1, the measurement is of z minus x or z plus x, one of the two. Of course, you know, I can just rotate the state unitarily, rotate the observables. That's why I'm saying it's up to local unitaries or up to local isometries if you want to be more precise, but it doesn't matter. I know that at this point, up to those local operations, this is exactly what Bill put into the devices. And if this is the case, so this self-testify for the state, and this self-testify for the devices. But this is, of course, a very idealistic scenario. So this is like Bill showing, you know, I'm 100% honest with you. If I see this, so if in running this Bell test, the CHS test, I really reach the probability 86 or around 85% or so, I know that the outcomes are truly random because they come from the genuine quantum measurements on quantum states. And there's just no way Bill could hide something or generate those devices in any other way. He wouldn't be able to do it without sort of messing up with this S value. If he violates the Bell inequality to this degree, he has to do it this way. Now, the interesting case and more complicated case, you may ask, say, well, you know, for this to be practical or to be of any value, you have to do the estimate for something that is, you know, if he's above 75%, but you know, not maybe 85, but somewhere in between. What can you do there? It turns out that it's possible to estimate, and let me just let me give you some kind of indication how it works, without going maybe too much into technical details. So what we know is that it's not very difficult to derive this, but you can derive, for this simple scenario, you can put the upper bound on the probability of guessing by Bill, and that is in terms of the violation of Bell inequality. It is something like, I hope I get it right. It's a very simple formula. And so it says that for the observed violation, well, if Bill wants to, let's put it this way, the base case scenario of what Bill can do is to operate with this formula. He can actually generate data that give you the S value here. And by doing so, you can see the trade-off. He's sort of limiting his degree of predictability. So let's see whether this makes sense. Let's look at the cases where S is equal to. So when S is equal to 2, then this is equal to 4. 8 minus 4 is 4. So then square root of 4 is 2. So this is half. So the probability of guessing is 1. Makes sense, right? So the Bill can guess if you operate with S between -2 and 2, Bill, it's possible, you know, the upper bound on his knowledge is the probability of guessing is 1. So if S is equal to 2 square root of 2, so then the square of that is equal to 8, this is equal to 0, so Bill probability of guessing is half. So he cannot guess, it's just a random guess about the bit value. So this is a sort of like one can show this. However, you know, if Bill wants to be tricky though, he can still play with me. He can play in the following sense. So let's look at this diagram again. So we have a situation here where for S equal to square root of 2, we show that this is kind of a pure case. Where S is somewhere here, so then we cannot identify what Bill is doing exactly, because there are various possibilities corresponding to S bar. However, we can have this estimate, by the way. But the question is, Bill might be doing something like this. He might be actually mixing two different behaviors. He might be going between, say, 2 and square root of 2. So placing the behavior here. So sometimes he would just generate maximally entangled state, everything fine, without having any knowledge, probability of guessing equal half. And sometimes we'll just put genuine data and would know exactly what is there. So how do we deal with this case? Would this be still valid? So it turns out that this probability of guessing is actually always okay. And this could be replaced by the observed value. So we have a situation where Bill is trying to mix different behaviors so that the observed value of S, let it be a convex combination, sum over K, P sub K, Sk. Then he cannot do better than that, and you can show this simply because of the convexity of this function. So let me explain it. So in this case, if he's trying different or mixing different behaviors with different values of Sk, so that I observe a certain average value of S, so then for Bill, that would mean the probability, his average probability of guessing would be bounded by sum over K, Pk, and I have this expression here. It will be half plus 1 over 4 square root of A minus A sub K here squared. And so let's take a look at this expression. So this is equal to, I'm going to have half plus 1 over 4 sum over K Pk 8 minus S sub K squared. Now, the interesting thing that this square root here is a concave function. So what it means that this function looks, if you take two values, so S1 and S2, it goes like this. So it's a concave function, which means that that if you try mixing, it's not going to help you, because if you try to do the mixing of this and this, you will end somewhere here. But the value of the function, in fact, you're better off when you're here. So in other words, the concativity of this implies, if you have a concave function, so then, the sum of Pk f of xk, in this case, is going to be always less than f of sum of the k Pk xk. So that's the definition of concativity. So when you apply it to this, you will get half plus 1 over 4, and then you have the square root of 8 minus, and you have sum over k Pk S sub k squared. So which is the observed values squared. So in other words, I don't have to worry about mixing approach. So even if Bill is playing with different values of x, having behaviors that are sometimes showing larger s, so he's trying to do something like this inequality still holds. It actually refers to the observed violation of the Bell inequality. Now, there's last point. So at this point, you can see that I hope I managed to persuade you, even though I use a bit of a hand-waving arguments to go, but you can fill the gap. You can just look it up, fill the gaps. But you have a rough idea how I can see, how I can be persuaded by Bill. So let's go back to this scenario and let's try to summarize where we are now. Because there is one last bit that I have to address before I let you go to the beach. By the way, this expression here also tells you what is the amount of sort of randomness one bit generated. So you take the log 2 in order to get the mean entropy. So you will have something, so it'll be 1 minus log to the 2, 1 plus 1 over 2, 8 minus s squared. So this is the ratio of, this is the amount of randomness per bit if you observe the violation of this type, right? So let's going back to this design. I got those devices from Bill, and X, Y, and I get outputs B and A. And so I got those two devices from Bill. I can press the buttons, input X and Y, and I can generate sequences, and I can then pick up those values. And if I see the violation in the SHSH test, I can estimate how much randomness there is per bit that was generated. In the extreme case, when S is equal to 2 square root of 2, I can take all the data because it's all random. But there are two points here. So actually one point here. As I mentioned at the very beginning, in order to run CHSH test, I have to choose X and Y randomly, right? So if I'm choosing X, Y randomly, that means I already have some randomness, some genuine randomness. So it looks like not a very efficient thing because I'm wasting lots of randomness in order to get this fraction of randomness per bit. But everything, if I were to do the testing, if I were to run CHSH test on every single pair, that wouldn't work. That would be stupid, actually. I don't need this randomness from Bill because I'm going to, I have some of my own. So why I'm just going to waste it just to verify that what he's doing is okay. But in fact, I will be getting at the end less randomness than I'm putting in. So the thing is, in order to be okay, in order not to waste randomness in this case, I still have to have some genuine randomness to do the testing. But the answer to this is, do not actually use random X and Y all the time. Do the spot check on bills. So the idea is, if you are going to generate the sequence, select randomly only a fraction of those and run CHSH test on them. And let's see whether this makes sense. So the idea essentially is, most of the time I put X equals 0, Y equals 0, or any other fixed number, no randomness, it's fixed. But every now and then I choose X and Y randomly. But Bill doesn't know which particular round will be chosen for this random test. So I'm going to do some spot checks here, maybe here, maybe here. And is this okay? Well, it turns out it's quite okay because of, again, Hüffing inequality, or Hüffing inequality. I'm still not quite sure how to, I have to ask some Finnish friends how to pronounce. And it just, so remember the estimate, so how far, so roughly speaking, the estimate value of S and the real value of S, how different would they be if I do only the spot checking? So if you want them to be different than epsilon in many runs, so the probability of this is bounded by 2e to minus 2n. Well, put capital N as a total number of things generated, epsilon square. So so suppose I'm going to only choose a fraction of n. So suppose I'm going to choose a small number of n to test, which is equal to q times capital N. So q, let me take q, which is 1 over square root of n. Okay. So in other words, my big N, my small n, number of those that I take to the test goes like the square root of n. So this, by the way, is so this is the number of things I'm going to take for the test. So I put a small n. And so this thing here then goes like the square root of big N, right? So this q is 1 over square root n, so this goes like a square root of big N. So I'm generating capital N, big N bits here. And I only do the testing on a fraction which is of the order of the square root of n. And you can still see that because the square root of n, okay, it's not n, but this is getting sort of a smaller and smaller. So this estimate is pretty good. I can get it as good as possible if I just, in asymptotic limit. So I'm getting sort of a quadratic randomness expansion here, going from square root of n. This is the randomness roughly in how many cases I have to put the random bits, plus, choosing the places. So roughly something of the order of square root of n. And I'm getting n random bits because even those that I measured and took for the test are valid random bits, right? So that is okay. In fact, we can do better than that. You can have a exponential expansion, but this is maybe the easier to explain. So you can see that what I'm doing, by doing the spot check on Bill, keeping Bill honest, I'm just going every now and then, choose randomly the places, and then for this, I check whether this condition, the CHSH condition, is satisfied. And I'm doing this on a sample of big N. I'm doing this only on the square root of n cases. And by this inequality that I cannot pronounce, this is still fine. And this tells you that you are doing a good job. So that's the first thing to address. The first thing is, okay, by doing spot checks on bills, I can still, I'm okay. I can trust him as long as he goes above this 75%, I can do something about it. And the last thing, of course, to address, which I'm not going to address, is to remove this IID assumption here, because obviously it's crazy. If you take adversarial view on Bill, why do you restrict him to IID scenario? He can do whatever he wants. He's a free man, right? He can. So in order to go beyond IID, you can do it. There are techniques, and so I ask you to maybe do it as the homework, not necessarily that you don't have to go into all technical details, but I'll give you sort of a pointer. So a pointer is that techniques that are used for randomness expansion, but also for security proofs, the whole thing here can be translated into device-independent key distribution, where instead of one person doing this check, there are two individuals doing this checks, and so on and so forth. Slightly different scenario, slightly more complicated, because there are two people involved, there maybe they have to communicate, there may be some errors. So the key rates are somewhat different than the randomness I get from those devices, but the concept is very, very similar. So once you understand one, it's not a big deal to understand more, the key distribution thing. But in those cases that the cases where the typical technique that is involved is to go to the asymptotic limits, and in the case of IID, that is known, that is a rather standard procedure. But in case of going beyond IID, there's a technique that is called EAT, which stands for entropy accumulation theorem, which is due to few people. But if you want to have a really nice, good explanation of this, you should just look up a woman who is called Rotem Arnold Friedman. So she gave a number of lectures, and her PhD thesis was essentially about proving the device-independent security of the device-independent quantum key distribution going beyond IID. So that's, and the good thing that she also gives very good lectures, so you probably find it somewhere on the website. Then you will have this explained, and using this EAT technique, you can go beyond IID cases. So I guess, this is the whole story that I have. So let's try to sort of like summarize what we said. So we have Bill, right? Bill has a company, says, I can sell you a random number generator. And has to be 2 boxes, Bill, 2 boxes. One I'm not buying. And then Bill also is very possessive about his technology. He says, I'm not going to let you even look into this box, but I give you 2 boxes, and then I promise that you can run a CHSH test, because those boxes are designed this way. So they have inputs which you can control. You can use your trusted random number generators. You control those inputs, and then you can check the outputs, and you can see that they are correlated in a certain way. And then I know that if Bill can achieve that, and that was this argument of me showing you the self-testing part, which was, hand-waving argument, but I showed you that if the function gets the maximum value for s equal 2 square root over 2 times square root over 2 times, 2 square root of 2, then essentially I know what Bill is doing. He's honest, he's putting qubits in maximally entangled state into those boxes, and I'm getting the data that I see. Then the second part of, later on I said, even if Bill cannot match this 2 square root of 2 limit, because usually he cannot, because there's a noise or anything. But of course, in this scenario, even if there's noise, I assume that there's no noise. I assume that anything lower than 2 square root of 2 is his action. So potentially it could be. So and then I didn't actually derive this result, the upper bound of the probability of guessing. I only showed to you that it makes sense in the limits, but it's not really a rocket science to derive it. It's very easy. You have to there's a result by Horodecki, the whole family from Gdańsk that wrote those early papers about quantum entanglement, and they have a paper which shows what is the maximum violation of Bell inequality for a given state. And from that result, you can actually put this upper bound on probability of guessing. So anyway, I use this upper bound, and I showed you that you can, even if S is somewhere between 2 and 2 square root of 2, you can still get some randomness. It's just like it will be less than per bit generated, but you still get some randomness. And then the final question was, okay, if the ratio is that for every single bit that the box generates, you get some randomness, but it's less than 1 bit on average, then it's not good because you need to waste the randomness to run CHSH test. And the final part, we say, well, actually no, because most of the time we just fix it. And we only do spot checks on Bill. Bill doesn't know which particular which particular round is going to be taken for the test. So he cannot a priori design devices in such a way that they will pass the test. So therefore, the spot checking and the famous Heffing inequality, by now I'm sure you will remember this Heffing inequality. At least, this would be a positive outcome of this talk, right? By this Heffing inequality, you can see that for sufficiently long, you can still on the spot check have a pretty good estimate of this S. So that's okay. So that's essentially you have a quadratic expansion of randomness. You put roughly, you put say S random bits and you can get S squared random bits out of that. You can use more sophisticated techniques. In fact, Thomas Vidik, Umesh Vazirani, and other people showed that you can even have exponential expansion. And this is sort of ongoing field and lots of interesting results. The step further, like where Vidik and others went, was that you don't even need that genuine randomness. In order to do spot checks on Bill, pseudo-randomness may work in some cases. So the amount of seed that you need may not be actually that huge for testing, for spot checking on Bill. And so remember our hero Bill from this lecture, who suffered all the time, but at the end, you're not evil because you can convince us that your devices are okay, right? Yeah. So any questions you may have about this? Well, as I said, yeah, please. Oh, yeah.
Yeah, before you mentioned that omega can go to 1, that's equivalent to saying that S is equal to 4. When you say S is equal to 4, do you have like a physical meaning on that, or is it like physically impossible to reach that?
Well, we don't know. So, okay, so the S equal 4. I think maybe you should answer this question. We have this ongoing joke here, you should one day explain it to them. So let me draw something that you'll probably see in the literature many times. Ooh. Okay. I'm sorry. I don't know. I didn't drink anything, honestly. What is this?
Just it's been a long time.
Okay, wait a minute. No, it cannot be like this, right? Slightly better. Okay, well, never mind. So this sort of like is illustrated. So this is a convex set that represents three different types of behaviors of boxes. So inside the square are all these classical boxes, and so they are sort of sandwiched between S minus 2 and S equal 2. So this is the classical set. Don't buy boxes from Bill if they show this kind of behavior. Now, if you move sort of, let's say, on this axis. By the way, this kind of cross section of those sets is very, very misleading. imagine, I mean, they're all in 8-dimensional space, in fact. This sort of set of classical correlation is rather simple. It's a polytope. The other one of the so-called non-signaling correlation is also a polytope, but the circle that is supposed to represent quantum type of behavior, it just circle here, but behind it is actually a real monster in terms of a shape. We don't even understand how it looks exactly. But anyway, so then if you go further, then it's just, you go to this T-Relson bound, 2 square root of 2. And this is actually all what we know today in terms of the technology that we can implement in the lab. As far as we understand quantum theory, as far as we understand the world, this is the best we can do. We cannot do better with quantum physics than this. However, you may still consider, it was interesting to look at behaviors that respect relativity, that respect locality in the sense that you don't have instantaneous communication from 2 different things. You don't have immediate impact from one part to the other. It turns out that the set of behavior is larger, strictly larger than the quantum set. You know, it could have been, and it would be actually a pretty nice result, that non-signaling behaviors, those that respect relativity, are exactly quantum behaviors. It turns out that quantum behavior respect relativity, but there are some other hypothetical behaviors that we don't know how to implement, but they still respect relativity. We call them non-signaling behaviors. So at the top here, the classical example of this non-signaling behavior is the one, is this CHSH condition. So that's the one that we talk about, so that A plus B is equal X not Y. If the boxes can satisfy this condition, you can still not communicate instantaneously using this condition. And it's very interesting we use this condition saying that this condition serves as a reference point for us. So we simply look how close, so for example, this figure, this omega, can be expressed as, I think, half, call this behavior n, scalar or inner product of any behavior with n. It just tells you how close you are to this magical correlations that we can never achieve. It seems that the best we can do is here. And the question is, why 2 square root of 2? Is there something special with 2 square root of 2, or this omega equal to cos squared over pi over 8? And we don't know. People try to, it's an interesting area of research where people try to relate this to something, saying, for example, oh, if we could do something better than here, some aspects of communication complexity would be different or something else. So people are trying to relate this to operational tasks. You can start thinking, what would the world be if you could have correlation, something there? One thing we know that you wouldn't be able to communicate instantaneously because those observe relativity, but maybe there is something that we can do better. And there are some conjectures about communication complexity and so on and so forth. But it would be wonderful to discover why nature picked up this particular point. We don't know. Yeah.
I know you said it represents like a more complex shape, but what's the, like, for the 90 degrees of where those hyperplanes are, what does that like represent? So like the
this polytope?
Yeah, so like the, instead of going like that, going like,
look, yeah. From what I know, it's just you get all possible shapes. It's, if you look at the quantum shape, it's not even smooth. There are some edges. All we know is it's a convex set. But apart from that, not much can be said. There are papers, and this is a topic of studies, I think still until now, looking at all kind of different cross sections, but this is an 8-dimensional monster that doesn't look nice in any way from any perspective you look at it. So I don't think we know much about it.
These are just the simplest convex shapes that we can think of. Just
Well,
draw this
you
as
know,
a little.
there is some work.
cartoon.
There are some. You can use some. We also talked with one. Sorry, what's your name? Yeah, we talk about this problem. Yeah. So we talk during the break about how can you have some sort of like envelope of this shape having some kind of different functionals, not only this S functional, Bell functional, but you know, there are some other different inequalities called tilted inequalities where you simply go in some other direction. That's what you were suggesting. So I can just, instead of slicing it this way, I can start slicing it in some other directions. And people did that. There's a beautiful area of, well, beautiful papers on the tilted Bell inequalities where you just slice it in a different way. There's also a hierarchy of approximations in terms of some sort of polytopes from the outside, where you can make sort of a tight envelopes. But you know, still, what we discover using those methods, so they're very useful. And so you can look up something that is called, I think it's called NPA hierarchy. This Navasquez, Pironio, Asin. They had sort of a set of approximations to this, and you can look it up, and that's a nice thing to know. But what we discover is just, it's still complicated. Yes, please.
Hello. Okay. So you mentioned that you can do like self-testing for the quantum set because it's convex and not a polytope. So then I'm wondering, can you? Is it only possible to do self-testing if it's convex and not a polytope?
Probably not. Probably as long as sort of like you can show that, you mean but the implication the other way around is probably that as long as you can pick up maximum and you can somehow prove that this maximum is unique, probably using other techniques that would also work. In this case, it's kind of obvious, right? So it's for convex sets, linear functionals get the max, and maximizer, minimizer are either hyperplanes or single points. And in this case, it's kind of easy. But I don't think it is the only, I cannot claim that this is the only way to do it. You can probably also consider nonlinear functional of some sort, where I guess I'm just speculating, okay? Maybe just nonsense what I'm saying, but I can easily just venture into something like looking for maxima and minima of some other functions, not necessarily linear functionals, and that would be probably still okay.
Thank you.
Yeah.
I was just wondering if you could quickly relate us back to your story from last time of this parallel story of curiosity and security, where this testing of, or like this kind of not trusting devices fit.
Yeah, so what, okay. So there's a bit of a history of the field. That's what you're asking for, how it happened, how this. Right. Right. So I think that Mina, you've covered BB84, right? From what I saw in your slides. Yeah, so what happened, historically was that some quantum cryptography popped up in two different ways. I think Steven Wiesner, who had this idea of conjugate coding, he didn't refer to any Bell inequalities. I don't think he even knew about this stuff. But he knew about incompatible observables. And so he came up with this idea of banknotes that you cannot forge. And Charlie and Gilles took it further, and they came up with the key distribution that Mina discussed, right? So that you have, this is usually like the scenario is that you have a sender and then you have a receiver, and you may have a eavesdropper in between. And by the fact that you cannot just perform the measurement that can distinguish between non-orthogonal states. You can try some Hellstrom measurements, you can try some other techniques, but there's a limit. You cannot beat Heisenberg uncertainty principle. But all this scheme relies on, it depends on the fact that you know exactly what the boxes are doing, that the preparation is a single particle, the detection is as it is. You can show that if those conditions are not satisfied, if the emission is not of a single qubit, but say 2 qubits, for example, or more, then the system is not secure. So it depends crucially on you knowing that or trusting the devices. So that's that's one part of the story. The part of the story that I was telling you about is a fusion of interesting research on the foundations of quantum. People like Einstein and others asking genuine questions. Is it truly random and therefore unpredictable? And of course, people working on crypto side. As I said, I didn't know about Charlie's and Gilles' work, but my interest was how to combine the fact that something is truly randomness and therefore unpredictable and use it for cryptography. Because if it is unpredictable to everyone, that's useful, right? So that means nobody actually knows about it. So that means you can generate the keys. So using techniques very similar to what I described today, even though in very naive way, because when you do something first time, you don't go into, it's very rare to have a very sort of like sophisticated way. Sometimes you go into very simple, you have a very simplistic approach to something, and it may not even be always right, but sometimes by a sequence of modifications, you finally get there. So that was sort of my way of doing this. And I have to confess that even though I knew that the system is somewhat better, because I don't have to, as compared to Charlie and Gilles, because I don't have to protect the source, I was not fully aware of the fact that it can be used as a device independent thing. Then somehow that you can also, that this violation of Bell inequality tells you something about the devices, that even if you go to the maximum, for example, there's only one way of doing this. Somehow I missed that point. Maybe I missed that. So it was only later that people, many people came up, like Tony Yassin was one of them, who just pointed this to me, saying, look, actually the system is probably better than you think it is. Which actually shows that sometimes your idea are more clever than you are, right? So you can come up with something and it starts living its own life. And so it evolved into this device independent and also, so it's a game changer, I think, altogether. So it's not, it's not, comparing the two is difficult because even though you can reduce, in the sort of early days, people thought, oh, it's only entanglement, what matters. Therefore, people look for reduction of entanglement base into BB84. But the going towards the Bell inequalities is just different. You cannot do device independent with BB84. You just have to use something like Bell inequalities. And there is other ways perhaps doing this, and the field is evolving fast. And what is interesting, though, there's experimental progress in the field as well. about in 2022, where Zeilinger and Alain Aspect and John Clauser, when they got the Nobel Prize for experimental testing of Bell inequalities. I think that there was a significant difference between the three of them, because Clauser and Aspect certainly were driven by curiosity. Anton already knew that it's important for applications, so that things like fixing loopholes was important. But anyway, the same year, shortly before that was announced, there were 3 experiments showing the proof of the principle for the device-independent crypto. And as far as I know, there's a beautiful experiment coming from our Chinese colleagues. They managed to show that you can really do device-independent quantum key distribution. So therefore, you can trust them as well. You can buy those devices if you want. At least they have a proof of the principle of this working over some distances. So this is like a story in a nutshell.
Maybe it's like these vehicles.
When I was talking about first time, so if you've got 2 qubits and they're separated, you may want to transmit that information to them instantly. Just imagine 2 ones up and 1 down, even if they're separated by parts of the application. So, is there any intuition for any protocols that you things we do in terms of qubits that you might get an advantage with the faster than light bound fields?
So
it's not the same thing.
I'm not quite sure I understood the first part. So you're saying that the way you think, or the way things were explained to you, when you have 2 entangled particles, you perform the measurement on one, and the other one collapses to a certain state instantaneously, right?
It's not, you can't transfer those.
Yeah.
So it's and that's why it respects relativity.
Yeah.
So that's not the same bounds of what is the max, the exponential, the outside square of the line.
Yeah. So first of all, yes, so that you can think, of course, about this collapse. As you pointed out, you cannot use this to transfer information, right? Because by performing the measurement on 1 qubit, you cannot enforce any particular outcome. So if we share maximally entangled state, it is certainly true that if I perform the measurement and I see outcome 0, then if it is the state 0, 0 plus 1, 1, I know that when you perform the measurement, you will get outcome 0. Because in this language of collapse, you can think about it this way: your qubit collapse into state, eigenstate 0. The thing is, of course, that I cannot, this is not the way of transmitting information, because if I want to transmit information, I need to choose whether it's going to be 0 or 1, whether by performing the measurement, I'm not choosing, the measurement's getting random results. Which brings you to the next interesting point, that randomness of this outcome is absolutely essential for not being able to transfer information. Had it be sort of like a tiny bias even in this outcome, you can construct a device that would allow you to communicate instantaneously. So somehow this locality, so this non-signaling enforces randomness. So there's a beautiful connection there. You can show that for this system, for quantum system to really respect relativity, it has to be random. I'm not so sure whether this was the essence of your question, but you know, there's a whole story about it.